Hello, this is Austin Wessels, and this is my Project 1 presentation for Analytical Dynamics. As you can see, I chose a double pendulum on a cart for my system to model with the Lagrangian approach. So this is what we're going to be talking about today. We'll be going over the problem description, some applications of this problem and why it's important. Then we'll get into the equations of motion for our double pendulum on the cart, and we'll look at some simulations, and then we'll wrap it up. So the problem description. You can see here we have our cart, which is this purple block here. It has mass m sub c, and it moves in the x-axis. You can see here x sub c is its horizontal displacement. And we have two pendulums, each with a mass that is concentrated at the end of the pendulum. On the first pendulum, we have mass m sub p1. The pendulum is length L1, and its angular displacement is theta 1. And the second pendulum, we have mass mp2, length L2, and its angular displacement is theta 2. So as you can see, there are 3 degrees of freedom for this system, xc, theta 1, theta 2. You could also look at it and say that each pendulum can move in x and y, and they are each constrained by the arm of the pendulum so that they only move in their respective theta directions. One other thing that's not shown on this particular image is you could have forces and moments applied to this pendulum. So you could put a force on the cart, or you could apply moments to the first pendulum, or apply a moment to the second pendulum. And, well, why would you want to apply a moment to a pendulum? Because you would want to manipulate a robot arm. So a robot arm is very similar to a pendulum. This one happens to be inverted. So this particular robot arm has a few more degrees of freedom than the one we're modeling today, although it does not have a sliding base. This simpler system here is very similar to this one. This one has a few more degrees of freedom, makes it a little bit more complex. Of course, there's friction and other real-world variables in here that we're not modeling. So let's get into the equations of motion now. And we're going to start off by looking at this velocity diagram. Up here you can see the horizontal velocity of the cart is given by x dot sub c. And the velocity of the first pendulum here is shown relative to the cart, and it's broken into its x and y components so that we can add those later. You can see that velocity of the second pendulum is also broken into its x and y components, and the velocity of the second pendulum is relative to the first pendulum, which is relative to the cart. So you can see where these equations of motion are going to start to get a little complex. So the kinetic energy, using our velocities that we were just looking at on the previous slide, the kinetic energy of the cart is relatively simple. Mass times velocity squared over 2. And this is the kinetic energy of the first pendulum. And you can see we have mass times velocity squared over 2. The velocity is a bit more complicated. Here we have the vertical velocity, and here we have the horizontal velocity. And you can see we have the velocity relative to the cart and the velocity of the cart. And then down here we have the mass of the second pendulum and times the velocity of the second pendulum squared over 2. So if we look at this, this is our vertical velocity. We have the vertical velocity of the second pendulum relative to the first, and the velocity of the first pendulum. Then over here we have the horizontal velocity of the second pendulum, which is relative to the first, and the velocity of the first pendulum relative to the cart, and the velocity of the cart. Potential energy is a little bit more simple. Because of the way the problem is constrained, the cart does not change its potential energy. So right here we have the potential energy of the first pendulum, and so we have essentially mgh, so it's dependent on theta 1, and then for the second pendulum we have its relative height, which depends on the first pendulum as well. So we see that theta 1 come into this term in the equation as well. So we're going to use the Lagrangian approach to solve this problem, and we have L equals T minus V, the kinetic energy and the potential energy here. So we're going to take partial L with respect to Qi, and we're going to subtract the time derivative of partial L with respect to Q dot I, and that's equal to Qi, which I believe is D'Alembert's principle. I'm sure I'm not pronouncing that right, but so down here we're defining what this Q term is, and it's essentially just each state variable. So we have Qi being x sub c, theta 1 and theta 2. Q dot I is simply the time derivatives of these states, and then we have our external forces that we could, forces and moments that we could apply to our system. And in this particular scenario, these forces were set, forces and moments were set equal to 0, so we're just letting the pendulum swing freely, and we're not applying any forces to the cart, and we're not applying any moments to the pendulums. So these equations are quite complex, which is why we have them broken down this way. So we have the acceleration of the cart, the angular acceleration of pendulum 1, the angular acceleration of pendulum 2, and then you can see the numerator and denominator for each of these equations are denoted with the particular subscript for that state variable. So we have the cart numerator and denominator, and the numerator for theta 1, this is the long equation. We couldn't even fit the denominator on the same slide there. And then we have the numerator and denominator for theta 2. So these equations here were all derived in MATLAB. We started with this L equals T minus V, inputting T and V, and using MATLAB to solve the Lagrangian equation here. And those equations of motion were input into MATLAB and Simulink. And here is a link to the video on YouTube for the simulations. So we have this video here. I have it pulled up, and I'll start here before playing the video by describing this system in Simulink. So all of the dynamics of the pendulum, the equations of motion, are in this block right here, and we're getting states out of the system, which would be the position of the cart, the angular position theta 1, the angular position theta 2, and then their time derivatives. So you can see we are set up to give feedback into the system, but all the gains are 0. And then over here we have the draw pendulum file, which actually animates the dynamics of the system. And then we'll talk through some of the simulation here. So you can see our initial conditions here. We're starting out pretty simple. Mass of the cart, mass of the pendulums, the length of the pendulums, gravity. So it's pretty simple and pretty tame. These numbers are in radians, so pretty small angles to start out with. So here's our cart, and the pendulum's just swinging back and forth. So it's a pretty simple case at first. Okay, so now we're going to change some of the initial conditions and some of the parameters for our pendulum. And so you can see here that we have a 3.5 radian initial position for the first pendulum and a 2.65 radian position for the second pendulum. So that means our first pendulum will be past vertical. So if this is our cart, the pendulum will go up and to the left, and the second pendulum does not quite make it past vertical, so it's going to be pointed to the right a little bit. And we added mass to the first pendulum, and we made our second pendulum a little bit longer. So now let's see what that simulation looks like. So you can see here we're getting a little bit more of that chaotic motion we would expect from a double pendulum, and then especially with adding another degree of freedom, the motion is quite chaotic. Okay, so those were the simulation videos there. And then last, we'll wrap it up. If you have any questions, you can email me down here. And when you see this PDF file submitted, there's going to be a link right here showing the video that you just watched. Thanks.